Hi there, this is Mrs. Sharp. We are going to go over just the first part of some notes for 3.7. Our learning target is to define what is meant by the strong force and explain how the strong force is responsible for the stability of the nucleus of an atom. So our question is, what is the strong force and how does it play a part in the stability of the nucleus of an atom? So here's a problem that we haven't talked about yet in our conversation about the nucleus, and that's that all the protons that are stuck together in that teeny tiny little nucleus are positively charged. So they should be repelling each other and trying to get as far away from each other as possible. But they don't. They stay in the nucleus together, and if the nucleus is intact, then those protons are not going anywhere. So to explain this, scientists came up with a term called the strong force to explain why the nucleus stays together. So the strong force is the force that overcomes the repulsive forces of a positive nucleus and keeps the nucleus together. And there's a strong guy. There's another strong guy. Shh, don't tell anybody that I think that looks like Huntley. So if I were to draw what this looks like, just very quickly, I would have, if I had two protons together in the nucleus, their positive force would be driving each other apart. They would repel. So we would call purple repulsive forces. So the nucleus should be all coming apart. But scientists call the strong force the force that's keeping them together. So what happens if the repulsive forces are stronger than the strong force? Well, if our arrows become bigger, if the repulsive forces get stronger, then the strong force is not going to be strong enough to keep those together, and the atom's nucleus is going to fall apart. This is known as radioactive decay or radioactivity. It turns out that the ratio of protons to neutrons is very important. So starting out at the beginning of the periodic table, you have a ratio of protons to neutrons of about 1:1. As you go farther up the periodic table, it becomes more like 1 to 1.5. So the ratio of protons to neutrons is extremely important in determining radioactivity and how stable the nucleus is going to be. So for example, a very stable atom of hydrogen is going to have 1 proton and 1 neutron. That's a 1-to-1 ratio. But as soon as you make it a 1 proton to 2 neutron, 1 proton to 0 neutron ratio, let's use helium instead. So let's get rid of this. In helium, you have a 2 proton to 2 neutron ratio. That's going to be a 1-to-1 ratio. But as soon as you add a neutron, if you make an isotope, now it's not as good of a ratio. It's not a 1-to-1 ratio, so it would not be as stable. So that ratio of protons to neutrons is very important. If the strong force isn't strong enough, just like we drew those arrows before, the nucleus is going to fall apart, and that's called being radioactive or radioactive decay. So that's a nuclear reaction where the nucleus falls apart. It's a reaction of the nucleus, and it's accompanied by radioactive decay. There are 2 consequences to this. When you have a nuclear reaction with radioactive decay, the atom is going to become an atom with a new identity that is more stable. So it becomes a new atom. It's not gold anymore, it's something else. And then you're also going to have radiation that's emitted, that comes out. It can be energy or a particle or both. So here is an example of a radioactive atom's nucleus. So this isn't really a radioactive atom. This is really a radioactive atom's nucleus. And that would be very unstable. And so this is the radiation that comes actually out of the nucleus. So radiation can be energy radiated, or it can be a particle that's radiated. It turns out that there are 3 types of nuclear radiation, and this should be a review from your 9th grade year. So first you have what's known as an alpha particle. You have a symbol that sort of looks like a little fish for alpha. Its composition, or what it's made out of, is 2 protons and 2 neutrons stuck together. So if you think about it, 2 protons would be helium, and a typical helium atom would have 2 neutrons as well. So there's no electrons, it would just be the helium nucleus. And if you have 2 protons and 2 neutrons, you'd have an overall positive 2 charge. Alpha particles can be stopped simply by a piece of paper, so they don't have a lot of energy, but their mass is very large. So they have a mass of 4 AMU, because remember, each proton and each neutron has a mass of 1 AMU, so altogether you would have 4 AMUs. The second type of radiation is called beta, and that's symbolized by the Greek letter beta, which is a bee with a tail. Beta radiation is made up of a high energy electron. So it's just an electron with a lot of energy, which means as an electron it would have a -1 charge. So in other words, it would take 2 betas to neutralize 1 alpha particle. A beta is stronger than an alpha particle. It has more energy. It can be stopped by metal foil, but its mass is much, much smaller. Since it is an electron, it has exactly the mass in AMU of an electron. And then finally, we have gamma radiation, which is high energy radiation that has no charge. It usually goes with alpha or beta, so you don't see gamma by itself. It's accompanied by one of the other 2, or maybe both even. And it isn't stopped by most things. So in other words, it has so much energy that it can't really be stopped. It would take several feet of lead or thick concrete to stop gamma radiation. And it doesn't have mass because it's not energy. It's not matter, it's just energy. So since it's energy, it's not made up of something that has mass and volume, so there's no mass. That's it for today. We'll talk about this more tomorrow. Thanks a bunch.